Hello all, welcome to the course Electrical Measurements and Instrumentation. In today's class, we will see electrodynamic or dynamometer type instruments. So here, related to dynamometer type instruments, we will see first operating principle, then construction, then we will see apart from construction and operating principle, we will also discuss its uh, torque equation and then advantages and disadvantages. So related to electrodynamic or dynamometer type instruments, so we can see that it is a transfer type instrument. So what is a transfer type instrument is, it is the one which can be calibrated with a DC source and then it can be used without any modification to measure AC. So that is a transfer instrument. So that means we can calibrate it. Dynamometer type instrument can be calibrated with a DC source and then without any modifications it can be used to measure AC quantities. So these are of very high accuracy. Electrodynamometer type of instruments, they are used both on AC as well as DC. So they can be used for measurement of AC as well as DC quantities. So mostly we use them in laboratories as ammeters and voltmeters for measurement of, for calibration purpose. So these are the standards for calibration of other instruments because their accuracy is very high. So as compared to PMMC and moving iron instruments, the accuracy of electrodynamic or dynamometer type instruments is very high. So therefore they are used as calibration instruments. Next, coming to their applications, so we can use them as voltmeters and ammeters, then also wattmeters. Apart with some modifications, we can use them as power factor meters and frequency meters. Now let us see the operating principle of electrodynamometer type instrument. So coming to operating principle, so you can see here, their operating principle is similar to PMMC instruments. So we have seen what is PMMC instrument. So these are permanent magnet moving coil instruments. So they have permanent magnets. We have seen the working principle also in the last lecture. There are permanent magnets and inside this we have a moving coil which is placed in between these permanent magnets. So this is the moving coil placed. So when current is supplied to this moving coil, so it will produce its own magnetic field. And also these permanent magnets, they have their own magnetic field. So due to the interaction of these two fluxes produced by these permanent magnets and the field produced by the this moving coil, so there is interaction of these two fluxes. So therefore the moving coil will deflect under the action of these two fluxes. So same working principle applies here also. But the difference here is, instead of permanent magnets, we used coils here. So you can see the construction. This is how electrodynamometer type instrument looks like. This is one view and this is other view of electrodynamometer type instrument. So these are the two fixed coils and this is the moving coil. So here also similar structure. This moving coil is placed on the spindle, or you can say it is a moving system, and attached to this spindle we have the pointer. So this pointer will show the deflection. So similarly here also we have fixed coils and moving coil. Moving coil is placed on the moving system. So we will see the construction of this. So before that we will see the operating principle of dynamometer type instruments. So these are very similar to PMMC type instrument. So in which the operating field is produced not by permanent magnets as we have seen, but by another fixed coil. So there are two fixed coils here. We also represent them by FC, and moving coil is there. So permanent magnet moving coil instrument, it cannot be used on AC currents or voltages. PMMC instrument cannot be used on AC currents and voltages. So it cannot be used for measuring AC quantities. Why? Because there the coil is not able to follow the pulsations in the torque because of the inertia of the moving system. So the pointer will not be able to follow rapidly changing alternating torque. So it will respond only to the average torque. So therefore, due to the changing or alternating torque produced, it will fail to show any deflection or reading. So in order that the instrument should be able to read AC quantities also, the magnetic field in the air gap, it must change along with the change in current. So this principle is used in electrodynamometer type instrument. So here if the direction of flux is reversed each time, the current through the movable coil will also reverse. So thus a unidirectional torque is produced for both negative and positive half cycles. So therefore in these instruments the field can be made to reverse simultaneously with the current in the moving coil if the field is connected in series with the moving coil. So therefore in this a unidirectional torque is produced. So here the average torque is not zero, even though we supply AC. So average torque is not zero and the pointer will show some deflection. Now coming to the construction of electrodynamometer type instrument. So these are the different parts of electrodynamometer type instrument. We have fixed coil, then moving coil, and then control system is there. Then moving system is there, and then damping system to produce the damping. Then shielding and cases and scales, these are secondary. So this is how, these are the fixed coils and this is the moving coil. These two are the fixed coils and this one is the moving coil which is placed here. And attached to this we have a pointer. So as the moving coil moves, or this pointer will also show the deflection on the scale. Now let us see function of each part. First one, fixed coil. So the field is produced by the fixed coil. So fixed coil, it produces the operating field. It produces the operating field. So it is divided into two sections. You can see in the diagram. It is divided into two parts. Same fixed coil is divided into two parts, and in between them we have a moving coil. So this arrangement is for uniform distribution of flux. So it is divided into two sections to give uniform field near the center, that is the moving coil, and to allow passage of the instrument shaft. Fixed coils are usually wound with heavy wire carrying the main current in ammeters and wattmeters. Next, moving coil. So a single element instrument, it has one moving coil. So function of the moving coil is to produce the deflecting torque. Deflecting torque is produced by a moving coil. So it is wound either as a self-sustaining coil or on a non-metallic former. So metallic, we cannot use a metallic former because that would result in eddy currents. So eddy currents would be induced in it by the alternating field. Both fixed and moving coils, these are air cooled. So both fixed and moving coils are air cooled. So because of this air cooled coils, the hysteresis and eddy current losses are reduced. So coming to control system or controlling, so control system, the controlling torque is provided by the control system. So this arrangement is done by, there are two control springs. So there are two springs. So function of the spring is to lead the current in and out of the circuit. So that is one function. And the other function of the springs is to provide the controlling torque. So these are the two functions of controlling system. Next to moving system, the moving coil is mounted on an aluminium spindle. So moving system, it carries the counterweights and there is a pointer attached to the moving system. Next, coming to damping. So damping system, damping is provided by this damping system. So in case of electrodynamic instruments, air friction damping is employed for these instruments and it is provided by a pair of aluminium vanes. So we have seen what is air friction damping. So nearly all the instruments are second order systems, so they will have oscillations before coming to the final steady state position. So it will have oscillations. So in order to damp out these oscillations, a damping system is required. To produce. So this damping system, it provides the damping torque. So we have seen the different types of damping torques also. Eddy current damping, then fluid friction damping, and the next one, air friction damping. So damping torque is produced by different arrangements. So we have eddy current damping, next one is air friction damping, and then fluid friction damping. So out of this arrangement is used in PMMC instruments, whereas in electrodynamic type instruments, so we can see here magnetic field is not very strong. So therefore we employ the cores are, the coils are air cored. So we employ here air friction damping is used. And it is provided by a pair of aluminum vanes which are attached to the spindle at the bottom. So these vanes move in sector shaped chambers. So eddy current damping is not used here because here the operating field is very weak. Next, coming to shielding. So we need to shield the instrument in order to protect it from the external stray magnetic field. So therefore, shielding is required, and this shielding is provided by laminated steel shield. So field produced by the fixed coils is somewhat weaker than other types of instruments. It is nearly 0.005 to 0.006 Weber per meter square. In DC measurements, even the Earth's magnetic field can affect the readings. Thus, therefore, it is necessary to shield an electrodynamometer type instrument from the effect of stray magnetic fields. So, therefore, air-cooled dynamometer type instruments, these are protected against external magnetic field by enclosing them in a casing of high permeability alloy. Or we can use laminated steel shields for shielding purpose. Next, coming to scales and cases. So there are wooden cases. These instruments are usually contained in wooden, highly polished wooden cases. So they are so constructed as to remain dimensionally stable over long periods of time. So the scales which are used, so pointer shows the deflection on the scale. So these scales are hand drawn using machine subdividing the equipment. So there are diagonal lines for subdivision are usually drawn for main markings on the scale. So most of the high precision instruments, they have 300 scale with 100, 120 or 150 divisions. Let us see the torque equation. We know that when a conductor, or you can say coil, carrying current is placed in a magnetic field, a unidirectional torque will act on the conductor or the coil. So let us illustrate it with the help of an example. So according to the construction, we have seen this instrument has two coils, fixed coil and moving coil. One is fixed coil and the other one is moving coil. So fixed coil is connected in series with this moving coil. So inside this we have a moving coil, and then it is again connected to the other end of the fixed coil. So fixed coil is divided into two parts, and in between we have a moving coil. So this is fixed coil and this one is the moving coil. Consider this is the fixed coil. Consider this is the fixed coil, and in between them we have a moving coil. Suppose that it carries a current in this direction, and this end of the coil carries a current in this direction. So this cross and dot, we can determine it by right hand thumb rule. So according to right hand thumb rule, it states that when you place a conductor in your right hand, then if the thumb points the direction of the current, then the curled fingers, they denote the direction of the field. So according to this rule, right hand thumb rule, if this is the direction of the current, so we can say that the direction of the field or magnetic field will be in this way. And then if this is the direction of the current, then we can say that the direction of the field is in anti-clockwise direction. If cross we have, if then the direction of the field is in clockwise direction. If dot, then that is the magnetic field direction is in anti-clockwise direction. So cross is nothing but it denotes that the conductor is held towards away from you, and dot means the direction of the current is towards us. So here cross is current is moving away from us, and dot indicates the current is towards us. So with this we can find out the direction of the magnetic field. Now here we have a moving coil inside this. Suppose this is the direction of the current is cross and the direction of the current is dot here, then the magnetic flux direction will be in this way. This will be in clockwise direction and this will be in anti-clockwise direction. So fixed coil will produce the operating field, and this moving coil will produce its own magnetic field. So this magnetic field, due to the interaction of these two fields, what will happen is the moving coil will deflect. Fixed coil will produce the operating field. Moving coil will produce its own magnetic field. Due to the interaction of these two fields, there will be a force acting on the moving coil. So the moving coil will rotate under the influence of these two magnetic fields. The moving coil will rotate. So there will be a force acting on this moving coil. So as the moving coil rotates, so attached to the moving coil we have a pointer. So the pointer will also show the deflection on the scale. Now let us derive the torque equation. In order to derive the torque equation, consider, so I1 is the instantaneous value of current in the fixed coil given in amperes. I2 is instantaneous value of current in the moving coil in amperes. L1 is self-inductance of the fixed coils, so that is given in Henry. L2 is self-inductance of the moving coil, so that is given in Henry. And M is the mutual inductance between the fixed and moving coil. So unit of mutual inductance is also Henry. So we know that when there are two coils placed near to each other, each coil will have its own self-inductance, and in between and associated with the two coils we have mutual inductance also between the fixed and moving coils, so that is given by M. Now we know that the flux linkage of fixed coil Phi1 can be written as Phi1 is equal to L1 into I1 plus M into I2. So next, flux linkage of the moving coil Phi2 can be written as L2 into I2 plus M into I1. We know that electrical energy input is given by, so electrical energy input is given by So Vi energy is equal to power is equal to Vi. So electrical energy is given by Vi into T. So for a small change in time, we can write it as E1 I1 dt. So V is nothing but E here. E2 into I2 into dt. So according to Faraday's law, we know that E1 is equal to, or V1 is equal to d psi 1 by dt, and we can write E2 as d psi 2 by dt. So we can substitute the value of 5 psi 1. So therefore we can write electrical energy input as electrical energy is equal to, so we have I1 instead of E1, we can write it as d psi 1 by dt into dt will get cancelled, plus I2 d psi 2 by dt into dt. So this we can substitute the value of d psi 1. So I1 into L1 I1 plus m into I2 plus I2 d into L2 I2 plus m into I1. Next, to take the differentiation of these two terms. So keeping this constant, so we have to differentiate it. So it will be I1, keeping I1 as constant, so dL1. So second time L1 is constant, di1. Similarly, differentiate it with respect to m as well as I2. So dm into I2 plus m into di2. So in this way, for the second term also, I2 into L2 into di2 plus I2 into di2 plus m into di1 plus I1 into dm. So multiplying this by I1, I2, you will get I1, I2 dl1 plus I1, L1 into di1 plus I1, I2 dm plus I1, m into di2 plus I2, L2 di2 plus I2 square here. This is L1. So you will get here I1 square. So I2 square di2 plus I2m di1 plus I1 I2 into dm. So this is the equation which we are getting. If you differentiate it, take the differentiation of these two terms. So from this, since L1 and L2 are constants, so that means we can equate it to 0. So dL1 and dL2, differentiation of a constant term is 0. These are constants. So differentiation of these two terms is equal to 0. So therefore we can write this equation. So wherever dL1 and dL2 terms are there, so that will be 0. So we can neglect this term. We can neglect this term. So the equation will be I1 L1 di1 plus I1 I2 dm plus I1 m into di2 plus I2 L2 di2 plus I1 I2 dm plus I2 m into di1. So neglecting these, we can neglect this and we can neglect this. So this is equal to 0. This term will become 0. These two terms will become 0. So remaining terms are I1 L1 di1. So that is what we have written here. So sum of the input energy to electrodynamometer instruments. So it is stored in the form of magnetic energy in the coil. So while the rest of the energy is converted into mechanical energy of the moving coil. So input we give here is electrical and the output we get is mechanical energy, and the whole of the energy is not converted to mechanical energy, but some part of it is stored energy. So that is stored in the form of magnetic field. So change in So we can write this equation according to the law of conservation of energy. So input electrical energy is equal to mechanical energy output plus change in stored energy. So same equation can be written as mechanical energy is equal to input electrical energy minus the change in stored energy. Now let us see what is the energy stored in magnetic field. So we know that energy stored in magnetic field is given by half Li square. So since there are two coils, so we have half L1 I1 square plus half L2 I2 square, and we have to consider the mutual inductance also. So M into I1 into I2. Now change in stored energy. So for us, we can consider a small change in stored energy. So this energy is given by D of the energy stored in magnetic field. So this D of this equation we can write. Now take the differentiation. So it will be I1 L1 dI1 plus I2 L2 dI2 plus I1 M into dI2. So here we have to take the differentiation with respect to L1. Second time we have to differentiate it with respect to I2 with respect to I1. Next in this case also we have to first differentiate it with respect to L2, next with respect to I2. Next for this also there are three variables here where you have to differentiate it with respect to M, with respect to I1 and with respect to I2 also. So here we will have three variables or three terms. So for this we will have two terms. So that is what written here. Differentiation half is constant. So we can write it as half L1. Differentiation of I square is 2 I1. Plus I square plus we can here differentiate it with respect to I2. So it will be 2I2 into dI2 by, next for the second case, half will remain as it is. So I2 square dL2 plus M into dI1 MI2, next MI1, this is I1, this is I2 plus I1 I2 into dm. So here also since L1 L2 are constants, so we can write dL1 is equal to 0 and dL2 is equal to 0. So therefore from these equations this 2 will get cancelled, here also 2 will get cancelled, same equation will get here. So this will be I1 L1 dI1, this here also I1 you have. Change in stored energy is given by D of this term. So when we take the integration differentiation of these terms, so we'll get the relevant equation is I1 L1 dI1 plus I2 L2 dI2 plus I1 M into dI2 plus I2 M into dI1 plus I1 I2 dm plus I square by 2 dL1 plus I square by 2 into dL2. So here we know that L1, L2 are constants. Therefore, we can write dL1 is equal to 0 and dL2 is also equal to 0. So here from these two terms, dL1 and dL2 terms will be 0. This one and this one will be 0. So remaining terms will remain as it is, I1 L1 dI1 plus I2 L2 dI2 plus I1 M into dI2 plus I2 M into dI1 plus I1 I2 into dm. From the equations 1, 2 and 3, so we can write that from this equation we can write mechanical energy is equal to electrical input minus change in stored energy. So we have derived what is electrical input. Electrical energy is given by this equation. So when you subtract this from the change in stored energy, so that is this equation, we will get I1 I2 into dm. So this is the equation for mechanical energy. We know that the equation for mechanical energy is given by I1 I2 into dm. Now let Td be the deflecting torque and d theta be the change in deflection. Then mechanical energy is given by Td into d theta. So deflecting torque equation is equal to Td into d theta. So mechanical energy, equating these two, we'll get. So under the influence of deflecting torque, the moving coil will try to rotate. So there will be torque acting on the moving coil. So that deflecting torque Td into d theta is equal to I1 I2 into dm. So from this we can write Td is equal to I1 I2 into dm by d theta. So from this equation we can say that the deflecting torque depends upon multiplication of instantaneous values of currents and rate of currents. Here there are two currents and rate of change of mutual inductance between the fixed and moving coil. So this is the equation for torque. Now let us consider two cases. We know that this instrument can be used for both AC as well as DC. So it is a transfer type instrument. We can calibrate it with DC and same instrument can be used for AC also. When DC quantity is measured, let I1, I2 be the currents in fixed and moving coil respectively. We have seen the deflecting torque is given by I1, I2 dm by d theta, where these two are the average values. Controlling torque here is provided by the springs. So we know the equation. Controlling torque is given by springs. Tc is equal to k theta. So when at equilibrium, when the controlling torque and deflecting torques are equal, so equate the controlling torque and deflecting torque. So we have k theta is equal to I1 I2 into dm by d theta. So from this we can write I1 I2 theta is equal to I1 I2 by k into dm by d theta. So here deflection is directly proportional to, so if dm by d theta is a constant, then theta is directly proportional to I1 into I2, the product of the two currents. When we consider AC quantity, when AC quantity is to be measured, so we have to consider the instant, let I1, I2 be the sinusoidal currents having a phase displacement of phi. So let this be current I1, let this be current I2. So they have a phase displacement of phi. So let I1 is represented by this equation I1 sin omega t, I2 is represented by Im2 sin of omega t minus phi. So we can write the instantaneous value of deflecting torque is given by Td Im1 sin omega t into Im2 sin of omega t minus phi dm by d theta. So for AC, the deflecting torque is nothing but the average torque. So it responds to average torque only. So therefore we can write deflecting torque is equal to 1 by t. It responds to average torque only, 1 by t integral 0 to t. So this is the average torque. Average torque is equal to 1 by t integral 0 to t into dt. So the moving system or the moving coil, it responds to the average torque only. So we have to consider the average torque. So that is given by 1 by t integral 0 to t td into dt. So we can write it as 1 by t integral td is equal to, here Im1 into sin omega t, Im2 into sin of omega t minus phi dm by d theta. So dm by d theta is a constant. So since it is with respect to omega, d omega t. So this is the average torque. So when you from 0 to t, so this equation can be written as 0 to 2 pi 1 by 2 pi. So this equation can be, when we solve this integration of 0 to 2 pi, Im1 sin omega t, Im2 sin of omega t minus phi with respect to d omega t, we will get I1 I2 cos phi. So this equation, so therefore the average torque for one period of time for one time period of the currents is given by Td is equal to I1 I2 into cos phi dm by d theta. We can write it as I1 I2 cos phi dm by d theta. So this is the equation for the average torque. Since for AC we have to consider the average torque, the pointer will respond only to the average torque. So the average torque is given by I1 I2 cos phi into dm by d theta. So here I1 is the RMS value of the current I1 and I2 is the RMS value of the current I2. I1 is the RMS value of the current I1, I2 is RMS value of the current I2, and if dm by d theta is equal to constant, so then we can write the equation as theta is proportional to I1 I2 into cos phi. So if I1 is equal to I2 is equal to I, then we can write this equation as it is proportional to I square. So this indicates that the scale is non-uniform. So we have a non-uniform scale when it is to be measured as a voltmeter or wattmeter. If I1 is equal to I at an angle minus phi and I2 is proportional to the voltage 0 degrees, then theta is proportional to I into V. Theta is proportional to Vi cos phi. So that is the power which is to be measured. So for this case, the scale is uniform. So when the instrument is to be used as a voltmeter or ammeter, the scale is non-uniform, whereas when it is used as a wattmeter, the scale is uniform. To measure power, the scale is uniform. Electrodynometer ammeter. So let us see the applications of these instruments. As an ammeter, you can see the arrangement here. So there are two coils, fixed coils and moving coil. So fixed coil is connected to the moving coil, and moving coil, the other end of this is connected to the other section of the fixed coil. So fixed and moving coil, they are connected in series, and you can see here this is connected to the load, and this is the supply voltage which is given. Here when it is to be used as an ammeter, all the coils are connected in series. So TD we can write it as, when it is to be used as an ammeter, if the current I1 and I2 are equal, we can write it as I square into dm by d theta. Here I is the RMS value of the current flowing in the fixed and moving coil. So current through the moving coil should not exceed 100 milliamperes. So ammeter may indicate correctly at all frequencies if the time constant L by R of two branches should be equal, as otherwise the current will not be independent of frequency. So this is an important consideration. So this shunt is used so that this ammeter can be used to measure larger magnitude of current. Next, electrodynamometer type voltmeter. Here you can see that this is arrangement for this instrument to be used as a voltmeter. So these are the two fixed coils connected in series. This arrangement is connected in series with the moving coil also, and then connected in series we have a resistance. This is highly non-inductive resistance. So here I1, I2 is equal to I. So TD equation will be equal to, deflecting torque equation is equal to I square into dm by d theta. So here also I is the RMS value of the current flowing in the fixed and moving coil. We can write I as V by Z. So here Z is equal to square root of R square plus omega L square. So as the impedance value is increasing, though I will be decreasing. So correspondingly theta also will decrease. So therefore, so I is decreasing, theta is decreasing. That means deflection is decreasing. So in order to avoid this, what we are doing is, so this R should be very, very greater than omega L. So R should be very, very greater than omega L. So that is an important consideration here. So in order that this type of instrument to be used as a voltmeter. So this is a high resistance value, non-inductive resistance value, which has to be connected in series with the moving coil. So these are the most accurate type of AC voltmeters because their instrument is low when compared to, so they can be used in the range from 10 to 30 ohms per volt. Electrodynamometer type voltmeters, these are the most accurate type of AC voltmeters, but their sensitivity is less here. But the sensitivity of these instruments is low when it is compared to DC instruments, and it ranges from 10 to 30 ohms per volt. Next, coming to the errors in electrodynamometer type instruments. So main sources of errors here are due to low torque to weight ratio. Second one is eddy currents. So next is external magnetic field, and then temperature change. So torque to weight ratio is here is very low because we know that the magnetic field is produced by the coils are air cooled. The coils are air cooled. So therefore the magnetic field is very low. So flux linkage per ampere in the moving coil, they are also few. So therefore deflecting torque is very low. So to produce a reasonable deflecting torque, the MMF of the moving coil must be increased. So MMF we can increase by increasing the current through the moving coil or by increasing the number of turns. So the current through the moving coil cannot be increased beyond 200 milliamperes. So because we know that springs would be heated very much, because with the help of springs only the current is entering into and out of the circuit. So if we increase the number of turns, so it will give rise to increased weight of the moving parts. So weight of the system will increase. So that will result in low torque or weight ratio. So low torque or weight ratio indicates heavy moving system. So in such case, the friction loss is more. Therefore, friction losses in these type of instruments, they are larger than in other types. So frictional errors are very high in this instrument. Next is eddy currents. The effect of eddy currents is to produce a torque as a result of coupling between the moving coil and the adjacent metal parts. So if the adjacent to the moving coil, if we have metal parts, so moving coil carries current. So there will be eddy currents induced in the metal part also. So metal in the coil supports and structural part is to be kept as minimum as possible. So any metal that is to be used should be kept away, and it should be selected to have high resistivity so that it can reduce. So eddy currents induced are reduced here. Next, external magnetic field. We know that the operating field in dynamometer type instruments is weak. So therefore these instruments, they must be protected from external magnetic field. Portable instruments, they use metal shields which serve to isolate the coils from external influences. So therefore we need to use some external metal shields. Laminated steel shields are used to protect the equipment from external magnetic field. Next to temperature changes, we know that there are coils used. So high currents are carried by the coils which produce heat. So self-heating of the coils, they produce errors. So high accuracy instruments, they contain temperature compensating resistors which tend to neutralize the effect of temperature changes. Next, coming to the scale of electrodynamometer type instruments. So we have seen that for when the instrument is to be used as an ammeter, theta is proportional to I square dm by d theta, and when it is used as a voltmeter, theta is proportional to v square dm by d theta. So this v is in turn proportional to the current. So therefore we can write theta proportional to I square dm by d theta. Scale of this dynamometer type ammeter or voltmeter is not uniform. So when it is used as a wattmeter, when this instrument is to be used as a wattmeter, the scale is uniform. Next, coming to the advantages of dynamometer type instruments. So as the coils are air cooled, so these instruments, they are free from hysteresis and eddy current errors. So they have a precision, great accuracy. They have very high accuracy. They can be used for frequencies up to 40 to 500 Hz. So lower range is being decided by the oscillations of the pointer. Next advantage is, so they can be used for both AC as well as DC, and they have very high accuracy, and hence they can be used as transfer instruments. So they have a low torque to weight ratio. So this is one of the important disadvantage of electrodynamometer type instrument. So therefore they have low sensitivity. Low torque to weight ratio gives increased frictional losses. So these errors must be minimized if accuracy is desired. So this can be attained by reasonable reduction in weight of the moving element, proper selection of materials for spindles and bearings. Another disadvantage is, so these are more expensive than either PMMC or moving iron instruments. So this we have not seen yet. These instruments are sensitive to overloads and mechanical impacts. Therefore, they must be handled with care. So this is one of the disadvantages of electrodynamometer type instruments. Another disadvantage is, so they can be used in the frequency range from 0 to 125 Hz to give higher accuracy. So after that, the moving system, it tends to follow the pulsations in the torque at low frequencies. Moving system tends to follow the pulsations in torque at low frequencies. Thus, the measurements at frequencies as low as 5 to 15 Hz becomes impractical. So measurements at these low frequencies require special structures with abnormal damping. Another disadvantage is they have weak magnetic field. So flux density is about 0.005 Weber per meter square to 0.006 Weber per meter square. So it is very weak as compared to PMMC instruments. So this is the flux density of PMMC instruments. So low value of flux density, it affects the operating torque, and therefore the meter sensitivity is very low. The operating current is large here, and therefore they have high power consumption than PMMC instruments. So this is one of the disadvantage. Power consumption is very high, and apart from this, they have a non-uniform scale. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.